I'm going to talk about the pilot aided channel estimation for 4x4 MIMO-OFDM in multi-gigabit wireless communication system. This works, it will be presented in a conference, namely IEECON at Hua Hin next month, and it will be published in IEEE anyway. You can download it, but it'll take a few months, to appear on the IEEE Explorer. My name is Kitsanapong Pansi, and my co-author, the first author is Vanali Bongtelas and Pulipong Sutisopapan, or the last author. I think everyone know that, especially who work in the data communication, the number of the traffics is increases every year, and the data is gained a lot in year by year, because you already know that we have AI, we have data center, and the data center is collects many hues of data. So the transfer between the server, between the network, we need a lot of number of traffic. So the communications must be fast, and the multi-gigabit wireless communication is needed in the very near future. But anyway, we can increase the speed by using higher order QAM, but I think it's very sensitive to noise and fading or distortion, let's say. We can also increase the MIMO. Now we talk about also massive MIMO, but the complexity to estimate the data, to estimate the channel metric is extremely high, I believe. So especially in the high speed, the channel estimation is very challenging. But in this work, that's what I focus on this work, to minimize the complexity of the channel estimation and gain more channel tolerance by using 4x4 MIMO-OFDM, for example, in this setup. So the topic is show here. The first of all, I would like to review the MIMO-OFDM. Then I will move to what I propose, which is channel estimation, and then the simulation results and analysis are shown here at the last talk, and the last one is conclusion. We talk about the MIMO-OFDM communication. There are two words. One is OFDM and one is MIMO, which are orthogonal frequency division multiplexing, and multiple inputs and multiple output. Multiple inputs means the number of antenna there is at the TX there are multiple antenna here. We say here is input, and from the channel here we say here at the receiver there is an output here, and it consists of many antenna. So the modulator and demodulator, we work with OFDM modulation. As you can see, if we have a very large antenna and we have very large pump, the detector and processing to recovery the data would be very high complexity. Yeah, and what I propose is I mean what I propose to reduce the complexity. I propose the singular value decomposite method. We can talk about this equation first to make it clear how it works. Normal and generally at the receiver we note which is written in vector y is equal h metric multiplied by x. X mean the tx symbol plus noise. Yeah. By by using the composite of h, we will get u, s, and v transport. Then at the tx, we can, if we know h, we can decompose it. Then if we pre-coding with the at the tx with v, as you can see here, or we transport here and transmit it out at the receiver. V and V transport here will cancel out automatically. You can see here the complexity can be reduced because we multiply by V transport, it will be identical metric from the property of SVD. And yeah, we remain U and S to come to subtract it from the receiver part. But anyway, S is only real, pure real, no complex parts. So just invert S is very simple because it's only real. To invert this, you can use quadratic, for example, algorithm to inverse the S. And then if we multiply this back to the received signal, which is already cancel U and V, we will get X back, which is what we want from the TX very easily. So this is very significant complexity reduction, and then we can implement it very easily. So we have to know H, right? Yeah, as I can see here, we have to know H. If we don't know H, we can decompose it to be U, S, and V at all. So how to estimate H? So it's very simple. If we transmit the pilot, for example, in this figure, the time slot 1, I transmit only x1 for the tx1 here, and the rest tx2, tx3, and tx4 I will put 0 here. If we can write the equation formula, US is very simple to see here. Y1, Y2, Y3, and Y4 at the time slot 1 will be H metric. In this case is 4x4 metric because I consider only 4x4 metric to give an example, and x1 here, and the rest is 0 here. If we multiply this metric, we will get h11 multiply by x1, s2, s3 and h4, sorry. So if we know x, actually we know, right, because it is the pilot, we can subtract it one by one, then metric h will be get very easily. So we will get h1, s2, s3 and h4 for the transmitter one. We do the same things, but we transmit x2 at the tx2 for the time slot 2 or the second time slot, and the rest tx1, tx3 and tx4 I will put 0. So we will get h 1 2, h2 2, h3 2 and h4 2, and we do the same thing for x3 and x4. So we will get all the h in the channel metric very easily. Anyway, we can improve the estimation of h by using moving average filter, where the h at the time slot 1, 2, 3, 4, but we try to transmit 1, 2, 3, 4 again in the consecutive time, maybe 16, 32 times, or 8 times, for example, and then average it. Then the noise would be reduced. You will see in the simulation result. So as you can see, here is only subtract by divide by x1 or conjugate it. Just conjugate x1. It's very simple to multiply it back to get h. And here only summation, and if we obtain it like 2 power n, then only rotate left or rotate right to make a division. So it's very simple to implement, especially in hardware. My PhD student will work on this in the future. So move to results. First of all, I would like to show you about the accuracy of the h metric by using the MSE quantity, where the simulation parameter is the number of subcarrier. It's 1074. Channel fading is selective fading channel. QAM order is 1074 QAM, and the bandwidth is 160 megahertz. The pilot insertion, by using my proposed, we need box type pilot insertion method, and the channel tab is 8 tab. As you can see, if we transmit only one time, the bit error rate, the MSE is can be estimate h when the SNR is increased. You can see, because the SNR of 40 dB, the MSE is around 10 to minus 3, but we can transmit 4 times, 16 times, 32 times and 64 times. As you can see, the MSE is reduced time by time. At the 64 time, S64 pilot symbol, you can see here, the MSE can be reached below around 10 to minus 5 here, you can see. But I also investigate about the what QAM can be used a good pilot. We start from 4 QAM, 16 QAM, 64 QAM, 256 QAM, 1074 QAM and to 492 QAM. We use this QAM as a symbol. You can see. Oh, sorry, it's wrong written. It should be 1074 here. Anyway, as you can see, if we increase the QAM symbol as a pilot, the MSE here is increased too, because we already know that the large QAM is the more sensitive to noise. So yeah, we can use 4 QAM or 16 QAM to be a pilot. I think is the best, like those two lines here, this one and this one here. As you can see here. Okay, so if we increase the length of the tab to see the performance, as you can see, the MSC to estimate the channel for 8 tab, 16 tab, 32 tab, they are the same, no, or maybe slightly the same. Yeah, nothing changed. I think it's okay when this is the average for 16 times. So the last result I think about, if we increase to 4096 QAM, what will be happen? Yeah, and compare between using SVD method and without SVD but no channel, what we transmit at the in the system. As you can see here, the bit rate by using SVD is better than without using SVD, as you can see here, for both 1024 QAM and 4096 QAM at the bandwidth of 160 megahertz. So if we apply coding here, then the bit rate would be 0 or less than 10 to minus 6, for example. Let's say we can get here maybe 5 bit for the maximum efficiency if we use coding. So 5 bit multiplied by 160 megahertz, it would be around 800 megabit per second, but we apply this 4096 QAM, and it would be 7 bit for the maximum efficiency on this modulation for order. So 7 mean around 1000 megabit per second somehow. So this is multi-gigabit communication system can be achieved. Yes, here is the conclusion. I have investigate the pilot edit channel estimation for 4x4 MIMO-OFDM, and I also make the average to minimize the noise, and as you can see, it is enhance the estimation accuracy. Simulation of course is very low, and the purpose for a simple design on the FPGA, and it's very suitable for practical development in the future multi gigabit per second. Yeah, okay, thank you very much.